Hello, we're going to be talking about section 2.7 in your book. Section 2.7 talks a little bit about resonance and gives you a basic introduction into that topic. Um, the write-up is pretty decent, so get that, give that a look. What we're going to do is together go through what I think is a good reason why we need to talk about resonance, and specifically um, what problems arise due to our attempts at communicating chemistry. So we need to start with bond line structures. Bond line structures, if you remember, are structures like this, where each vertex corresponds to a carbon, right? And this means in this molecule that I've drawn, there are 4 carbons. But if you also remember, there aren't just 4 carbons, there are also 10 hydrogens that I'm drawing in now. 5, 7, 10. C4H10. So with molecules like this, the bond line formalism way of drawing is meant to allow us to communicate about the molecule, and it's not necessarily the most true form because we just drew the lines. However, the hydrogens are implicit there. They are not shown. And this is not the only place that bond line structures have a hard time accurately representing what the molecule actually is. So another way that bond line structures struggle is in multiple bonds, like a double bond. So in multiple bonds, what we see is that there are 2 bonds there signifying that there are 2 p orbitals that are being used to make a pi bond. Well, that's all fine and good. We talked a little bit about MO or about pi bonds through MO theory in chapter 1, but we kind of left it there. In the problem is that if you just look at this drawing of a double bond, we assume that there's a constant bond between these p orbitals due to overlap, and that's mostly true in this single case. But when you start building more double bonds that are in a row through resonance, such as this, where now you have alternating double, single, double bonds. Now each of these double bonds are actually considered um, through resonance to communicate with each other. And not only that, but electrons in, say, this pi orbital or this one can directly communicate or move into this orbital or this p orbital. And the bond line formalism doesn't give a good explanation for that type of reactivity or that type of electron movement, because what we have is a static structure, and we aren't taking into account any electron movement at all. In fact, that type of movement has a special name, and it's called resonance. Resonance is the term that we use for the movement of these pi electrons, such as this. And the reason why resonance is important is because um, without talking about the movement of pi electrons, we would completely miss the reactivity that could come from this structure here. Because in this conjugated molecule, the reactivity is not simply cut and dry like you see for this first structure. It's actually a mix of the two. And so you get kind of a hybrid of these 2 structures, not just the one. It's a major drawback to bond line structures, and something that we need to keep in mind as scholars in organic chemistry. Now, what we can do is talk a little bit about how this arose. So let's quickly flash back to what we talked about in chapter 1 when we brought two p orbitals together to make a double bond. So we had a p orbital here and one here, and we said that both of these had an electron, and they were going to come together to make an energy level of lower energy and an energy level of higher energy, right? And through the linear combination of atomic orbitals, we learned that if you mix two orbitals together, two atomic orbitals, to make a bond, then those orbitals disappear, and instead you get two molecular orbitals. And those molecular orbitals can then hold their own electrons. And this orbital is now a molecular pi orbital. And using the three rules, the Aufbau rule, the Pauli exclusion principle, and Hund's rule, we knew to put in these electrons in the lowest energy level and pair up those electrons if possible. And so we said that the structure of that bond, how it actually looked, was like this, where you had overlapping phases between two p orbitals on neighboring carbons. And the non-bonding orbital did not have overlapping phases, if you remember. And because of that, we said that there was a node present and there was no bonding event that occurred. There was only antibonding that occurred. So the last thing that we had to learn from this MO diagram is that this bottom level with electrons here was called the highest occupied molecular orbital because it is the orbital with the most energy that still has electrons inside of it. While the other one was called the lowest unoccupied molecular orbital because it was the lowest energy level that did not have electron inside of it. Now, specifically, when we're looking at bond line structures, we can actually understand we can understand how the reactivity of a conjugated system might be different than a simple static bond line drawing like this. Because again, this drawing does not tell us what specific orbitals are bonding and what specific orbitals are antibonding, much less which molecular orbitals are really the most reactive or where the electrons even are typically in this system. So we can use our flashback knowledge and say that instead of mixing two p orbitals this time, we're going to mix four p orbitals, one on each carbon. So we're going to take 4p atomic orbitals and we're going to mix them together to get 4 molecular orbitals. Okay? So let's do that. So we know that we're going to have, let's see, 4p orbitals, 1, 2, 3, 4. They all have one electron inside of them. There we go. And when we mix them all together, we're going to get a very low energy, less low, much higher, and a very high energy state. So let's look at what these actually might be in the same way as we did above in the molecular orbital diagram. So after drawing out 4 of these, there we go, there's our carbon skeleton as we had before. And this came from there. Then we can draw in, then we can think about how to actually put on the new molecular orbital, or the p orbitals to make up each molecular orbital. So in the original, we said that the most stable was the one that had the most overlap between orbitals. So let's do that. Let's give the bottom one a lot of overlap. Oh, actually, let's do this. There we go. So we'll have the bottom one with complete overlap of their p orbitals. There we go. So that looks very stable. And because of the three rules of putting in electrons into molecular orbitals, the Pauli exclusion principle, the Aufbau principle, and Hund's rule, we know that the bottom orbital is filled. Okay. Again, in the flashback, we said that the next most the more unstable version of that pi bond was one where there was less overlap. It had a node, right? So why don't we put a node into ours to make this a little higher energy? So we'll put in this node, we'll put in a node in the middle here, and it has to be in the middle because it has to be a symmetrical system. There we are. And there's a node right through the middle. And again, through the three rules of putting in electrons, we know that there is that's filled. Okay, so if one node destabilizes the system, maybe we should put in another to find the next energy level. So we can do that. We'll put in two nodes this time. Oh, whoops. There we are. There we go. Okay. Now this will give us two nodes. No overlap between those two, and no overlap between those two. And now this orbital is not filled because we only had 4 electrons, and we've already used those 4 electrons. Okay, so we started with 0 nodes for the most stable, 1 node for the second most stable. The lowest unoccupied molecular orbital has 2 nodes, so it seems like we need to add another to give us 3 nodes, right? There we go. We'll just do totally not overlapping bonds here. And that is 3 nodes. Okay, so now we know that this one is the HOMO, the one with one node, and the other one is a LUMO. So without understanding the drawbacks of a bond line drawing, we would have never known that in this molecule, really the reactivity is much different than we have drawn here, because you can have one of these molecular orbitals that has complete overlap, but another where there's only overlap on one side or the other. So the reactivity of this molecule would not be totally clear, and in fact, it's the reason why we have what's called a resonance structure that we can draw. That looks like this. And notice that what I've drawn has it is in brackets first. Those are called resonance brackets. In the middle of these two is a resonance arrow, a double-headed arrow that we use to signify that these electrons are constantly moving, and there's no real one structure that we're talking about. And note that electrons traveled in the first, in the top one here, but they travel back on the bottom because, again, the electrons are constantly moving. So you can see here now, with the combination of these two bond line structures, these two resonance forms, now we have a better understanding of what the reactivity patterns for the molecule might actually be, and a little better understanding of what the true structure of this molecule should be considered as. So this was a small detour into where bond line structures aren't necessarily the best choice for representing a molecule. And that's really important to know because we are communicating about molecules and we need to understand the drawbacks of any communication system or representation system that we're using to talk about molecules. So this has been chapter 2.7.